important concepts. There is time, there is space, and there is speed. In classical physics, those three ideas are unconnected. In special relativity, they are intimately connected because time will become dilated or lengthened, space will become contracted, and it's all due to the fact that speeds will approach the speed of light, which is a constant. So we're going to look at each one of these and then connect them together with speed. So first, time. Time is the time dilation factor, which is delta t is delta t0 divided by the infamous square root of 1 minus v squared over c squared, where delta t0 is the so-called proper time. That is the time between two events. That's what we mean by proper, is the time between two events that happen at the same place. In a given inertial frame of reference. Delta t0 is the time between the same two events. Delta t is the time between the same two events as seen or as measured in a second inertial frame of reference. And the key thing is, in classical physics, those two times would be equal. In special relativity, they are not, because speed v right here, this speed is the relative speed between the two frames of reference. And that will determine the relative time between the two events as seen by observers in the two frames of reference. Okay, the next thing we have is space. And space is contracted using the length contraction formula. It looks quite similar, except the square root is on the top rather than the bottom. L0 is the so-called proper length. And that is a length measured simultaneously in a given frame of reference. So here, proper means the length is measured, oops, spelled wrong. Simultaneously. Notice proper time was two events occurring at the same place. This is a length that is made at the same time. And that's what we mean basically by using a ruler that is at rest. When we use a ruler at rest, we can measure the length simultaneously using opposite ends of the ruler. L would be the distance between two events. As measured in a moving frame of reference. Now, of course, it's an inertial frame of reference. So here you're trying to use a meter stick that is moving, and you're trying to measure two events that are happening in another frame of reference. And the key thing is, those two distances are not the same. The reason they're not the same is the two frames of reference are moving relative to each other, which brings us to speed. That is just v, which is always equal to distance traveled divided by the time interval. Key thing now is these must both the distance, delta x, and the time, delta t, now must be measured in the same frame of reference. And that frame of reference, of course, must be an inertial frame of reference. Now what we're going to do is take a look at, well, what happens when I measure distances and times in different frames of reference? Generally speaking, we have two frames of reference. We have, for an example, a lab frame of reference. I'll draw a ground, and right here we'll put a building. This right here will be our lab. It will be on the ground. Then we have to have something that's moving at high speed, that is typically seen as basically a spaceship that is moving at high speed. And it is moving at some high speed relative to the lab. Of course, from the spaceship's point of view, the lab is moving in the opposite direction at high speed. And relativity says it doesn't matter who's moving and who's not. All we're saying is they're moving relative to each other. So we will define a lab frame of reference, and this will be our ship frame of reference. And those two frames of references are moving relative to each other. So therefore, we can calculate the speed that the ship is moving. So we'll call this the speed the ship is moving relative to the lab. Now, people in the lab frame of reference will measure that speed as the distance traveled, according to them, in the lab, divided by the time interval in the lab. So that's perfectly valid. Both distance and time are measured in the same frame of reference. Well, people in the ship can also measure how fast the lab is moving in the opposite direction. Turns out they're going to get the same speed, but we'll call it a prime just to give it a different designation. And this is the speed that the lab is, I'll put quotes because this sounds kind of weird, is moving relative to the ship. Because from the ship's point of view, the lab is simply moving in the opposite direction. We won't worry about signs. We're only looking at speeds here, which is a scalar. And that is equal to, well, the ship is making the measurements, so they have to use their rulers, and they have to use their clocks. Now, those two speeds should be equal. Namely, we should show that v equals v prime. To do that, we need to note that somebody's time is dilated and somebody's length is contracted. And when we take both effects into account, we can show that both speeds are the same. So, let's first look at the ship. So, the velocity relative of the lab as seen by the ship, the velocity of the ship as seen from the lab point of view, this is equal to delta x as measured by the lab, and it's delta t as measured by the lab. Now, the lab can watch the ship just move right by. You could easily see, here's the ship right here, moving in this direction. There's the ground. We could put a marker right here. We could put a marker right there. And this right here would be the distance traveled according to the lab. And that would be easily measured, if you will, at rest. This could be seen as a proper distance or a proper length. The problem they're going to have is measuring the time, because the time would be measured at two different places. Because we'd have to have a clock right here, and we'd have to have a clock right here, and they have to use two separate clocks. And some time would have passed between them using two different clocks. So their time is not the proper time. So delta t lab is not proper. The delta t that is proper would be the ship's clock. Therefore, we can relate the delta t that the lab measures to the delta t that the ship measures, because it'll be equal to the proper time, and the clock that would be on the ship would stay on the ship, and it would measure the time in the same place on that frame of reference. So this is the proper time. So delta t ship divided by, again, our wonderful square root of 1 minus v squared over c squared. So this now can give us the speed that the lab measures the ship moving. So put it all together. V would equal, again, delta x, according to the lab, that's a proper length, divided by delta t of the lab, which is not proper. So I'm going to convert that into delta t ship. And then we have to basically divide that by the square root of 1 minus v squared over c squared. So that is our formula for the speed of the ship, relative to the lab. Both using a proper distance and a proper time. Now, we have to do the exact same thing for calculating the speed of the lab relative to the ship, which is moving backwards as far as they're concerned. Now, they're using a proper time. So their delta t is a proper time. But notice they're going to have a problem measuring how far the lab has moved, because the lab cannot be easily seen as being measured from a ship that's moving away from it. So they have a problem measuring it. They can't measure the distance simultaneously, so they're going to have their delta x ship will not be a proper length. They will see that distance as contracted, so delta x ship will equal delta x lab times the square root of 1 minus v squared over c squared. It will be contracted. So right here, I'm going to put in the delta x lab, the proper length, times the square root of 1 minus v squared over c squared. And we can look at these two formulas, and the only difference between them is here the square root appears on the top, and here it's a reciprocal on the bottom. So therefore, these two things are actually equal. They will disagree on the distance traveled, they will disagree on the time that it takes, but they will agree on the ratio. The way we can look at that is that from the ship's perspective, they see, if you will, a long distance divided by a dilated time. V prime, which is what the ship sees, they will see a contracted distance divided by a long time. Excuse me, by a short time, because it's not contracted. A short time. And these two ratios will be equal. A big distance divided by a big time will equal a short distance divided by a short time. They will agree on how fast they're moving relative to each other, but arrive at that conclusion differently. And that is why special relativity works. They disagree on trivial things, distances and times, but agree on something they can both measure, their relative speed.